Okay, so we're moving on to section 5.5. This is still a part of the review from last semester. You should have seen these types, or this section last semester. This one is section 5.5, the substitution rule. So until now, all the integral problems we've had have had to be really easy. That's something that you can look at and say, okay, I know an antiderivative for that. I can do this problem. Now we're going to move on to some to a more general, or sorry, to a different kind of integral. And just before I introduce it, I wanted to kind of point this out. So, when we were doing differentiation, differentiation was pretty easy. If I handed you something, you would have, you might have to do product rule or a chain rule, but whatever I handed you, it was you could probably differentiate it pretty straightforwardly. Integration, going backwards, is a lot more difficult. The reason being is it's harder to guess, or it's harder to guess an antiderivative than it is to just differentiate something. And we're going to see that, especially in this section. So for the U substitution rule, this works. So this is going to be something that works for integrals of the form. I'm going to do it kind of generally first, and then we'll move on to some more concrete things. So if I have a function that looks like this, composite function f of g of x times derivative of g, then this is something I want to use the U substitution for. So what this is really saying is I want an integral where a function and its derivative appear. And that in this case is this g of x and g prime of x. So what I can do with this kind of integral is I can do what's called a U substitution. The reason it's called U substitution is because when we're going to see in a second, but we always use the letter U to change variables. So let's do it generally first, and we'll see some examples. So if I have this f of g of x, g prime of x, dx, I can let U equal to g of x, and I'm going to compute the differential du. So you can think back to you can look back at your formulas from Calc 1, but all that's going to happen is I'm going to differentiate this thing and multiply it by dx. Now you'll notice that what I have here, so here I have a g prime of x dx, just like I have here, and I think I've gone off screen a little bit. There we go. So what I can do is I can replace this g prime of x dx just by du. What this ends up being now is the integral g of x is just u. This is going to be f of u du. And now this might be simpler, and it might be, the idea is we want to do this in order to get something that's a little easier to integrate, that we can just look up in a table or remember our antiderivatives. But let's see some examples here. Okay, so move to a new whiteboard. So we have our first example. So we have the integral x cubed cosine x to the fourth plus 2 dx. Okay, so the way you want to handle these problems is you want to start looking for, so you can try and write it as f of g of x and then g prime of x. But all we're really asking you to do is we're asking you to find a function and find its derivative somewhere. So if I look at the inside of cosine of here, I have this x to the fourth plus 2. And if I think about, what am I going to get when I differentiate that? Well, if I differentiate x to the fourth plus 2, I'm going to get 4x cubed. You'll notice that the x cubed appears here. So that seems like a good place to start with our U substitution. So for this one, we're going to try letting U equal to x to the fourth plus 2. And when I find the differential du, this is going to be 4x cubed dx. So what I'm going to do, and not everybody does this, some people try and group together the x cubed and the dx. I'm going to solve this one for dx. And when I do that, I'm going to get dx is equal to du divided by 4x cubed. Okay, so now that we have dx, we're going to take this dx, so we've solved for dx. We're going to plug it in here. So what I'm going to get is going to get the integral x cubed cosine of x to the 4th plus 2 dx. And let's go ahead and plug in all the things we have. So you'll notice that x to the 4th plus 2, this here is u, and that's all that we're going to plug in for dx here. So this is equal to the integral x cubed cosine of u. Dx is now du divided by 4x cubed. And what you'll notice happens here is I have an x cubed up top here, an x cubed in the denominator. These are going to cancel. I'm going to get the integral. So this du over 4, I can make just a 1/4. I'm going to get 1/4 cosine of u du. And now if I pull this 1/4 out, 1/4 the integral cosine of u du. This integral is now, I can do pretty simply. So if you look back at the beginning up here, you'll see that, this integral, you're not going to be able to think up an antiderivative for it very easily. But this one I can do pretty easily. Integral of cosine is, of course, sine of u plus a constant. I'm about to make a new whiteboard. So if you want to pause and keep writing, go ahead. So the last step we don't want the answer in terms of u. Sorry. In terms, of u, we want it in terms of x. So I'm going to get 1/4 cosine of u plus my integration constant. If I plug in for u again, it's going to be 1/4 cosine of x to the 4th plus 2 plus a constant. Let me double check to make sure that I got correct value. Yeah. Yep. So that would be. So that would be the answer. So again, the problem. So that's the answer. The problem comes down to, in the beginning, you have to be smart about what you pick. You want to look for something that when you differentiate it, the other function appears. So I looked at this x to the 4th plus 2. I said if I differentiate that, I'm going to get a 4x cubed. X cubed appears here, so that's going to be useful. And when you do the correct u substitution at this step, so at this step, all your x's should cancel out. Everything should be left in terms of u, and you should be left with an integral that you can do. So let's do another example. So the rest of this is just going to be examples, just seeing some how these things can get more complicated. Okay, so let's do an example. So let's find the integral x over the square root 1 minus 4x squared dx. And again, you can look at this and you can automatically see, okay, I'm not gonna, think of an antiderivative just by staring at this. Maybe eventually you could, that gets kind of easy when you do these enough. But for now, we're going to need to use U substitution. So if I look here, I'm looking for, something when I take its derivative, I get what's left in terms of x. So if I look at the thing inside the square root here, and I start thinking, okay, if I take that derivative, what's that going to be? If I take that derivative, I'm going to get negative 8x. And up top here, I have an x, so that seems like a good U substitution. The one thing I should point out is when you're doing U substitution, it might not always happen that you pick the right U substitution. Maybe on the next video, I'll do an example where I purposefully pick the wrong U substitution so you can see what happens. Okay, but here I can figure out what U needs to be. I already pointed out the 1 minus 4x squared. That gives me du is equal to negative 8x dx. Again, some people group things together, and I think it's easier to just solve for dx. So this gives me dx is equal to negative du over 8x. So I can use all of this now, and I'm going to get this is equal to the integral. So I leave the x alone. So square root of 1 minus 4x squared now just becomes the square root of u down here. I'm going to replace this dx. Let me separate this. I'm going to replace this dx in terms of du. So I'm going to get negative du over 8x. And now I'm going to, clean things up and simplify. So make a new page. And of course, I've just forgotten everything that was on the previous page. So we have x over square root of u, negative du over 8x. So if we do some more simplifications, I can pull this 1/8 out. And again, we see we have an x up top and an x on the bottom. So this is going to be, I'm going to go ahead and pull the minus sign out in front also from the du. This is going to be 1 over square root of u du. And again, you can see that we've done this and we've gotten a function that's a lot easier to integrate. So let's go ahead and finish out the integration. This is negative 1/8 integral. So remember, square roots are fractional powers. If it's in the denominator, it gets a minus sign. So I'm doing negative 1/8 the integral u to the minus 1/2. So now I do the the reverse power rule. Get negative 1/8. Negative 1/2 plus 1 is 1/2 divided by 1/2. So doing some cleaning up, I'm going to get negative 1 over 4. Sorry, I forgot my plus c up here. Again, be careful with that. It's super easy to forget. Okay, so if I do some cleaning up, I'm going to get 1/4 u to the 1/2 plus c. And again, so I don't want this in terms of u. I want it in terms of x. So I'm going to take this u. I'm going to take this u. I'm going to replace it with my x here. So my function of x. So u is 1 minus 4x squared. So I have u to the 1/2. So that's square root of 1 minus 4x squared plus a constant. And that would be the end of that. So I'm going to wrap up the video here. I'm going to do a couple more examples in the next video. One where, I'm going to pick the, so we're going to see one where, I do a U substitution that requires me to do a little more work, and then one where I pick the wrong U and see what happens there and what the signs are that I picked the wrong U there. So that'll be it for this one.